Okay, so we are now ready to look at the exercises at the end of section 3.6. So this is the first one. Prove that if these two equivalence classes A comma B and A prime comma B prime, if they are equal and these two equivalence classes are also equal, then the product of these two equals the product of the other two. So you understand in what context this question has been asked. In the context of our theorem, the only theorem that we have in this section, where we were constructing the field of quotients of a given integral domain. So this essentially asks us to prove that the multiplication we defined in that set F of, in the set F of all equivalence classes, that multiplication is well defined. That's what has been asked here. But since we have already proved it in the actual proof, so it's already done for us. So in place of solution, you can write we have already done it. The first few exercises are like that. Exercise 2. Prove that distributive laws in F. This also is a part of the proof that we have already carried out. So here also our solution is the same. Then exercise 3. Prove that the mapping phi from D into F defined by phi of A equal to this is an isomorphism. Is an isomorphism of D into F. Okay, sorry, I cropped it. Now in this one also we have done, but this A comma 1, this looks somewhat unfamiliar. I don't think I have mentioned about A comma 1, because if you remember, we started with the integral domain D, which does not necessarily have a unit element. So what is this 1? Actually this whole notation represents something else. So we write a remark here, or we, in place of solution, we can write we have already done it. In fact, now here is the remark. We have proved that when D is a non-zero integral domain and G not equal to 0 is an element in D, then the mapping, since they are calling it by phi, let us give our mapping a different name, although there in the proof we called it phi, but to distinguish between these two, we call it, let us call it psi. The mapping which maps any element in the integral domain onto this, G, is an embedding. Embedding means an isomorphism. The element AG, G belonging to F, which actually does not depend on the choice of G, is denoted by this. We have already seen that irrespective of our choice of G, whatever G we choose, say for example, if instead of this particular G we choose something else, some other non-zero element, then these two equivalence classes turn out to be equal. And this was also the reason that the map we defined in the proof, that is actually well defined. So this element that actually does not depend on this choice of G is denoted by this symbol. That's it, nothing else. In fact, in the text, the proof mentions this. I have not mentioned it while proving the theorem, but it does not matter. That's the thing. Or we can write, we can further write a little more, that is, this is defined to be equal to this. And this is our remark actually. We have already done it. This is the for the solution and the rest is remark. Okay. Now we come to some exercise that we will actually have to solve. So here comes exercise 4. prove that if K is any field, containing D. So D is our integral domain and K is some field which contains D. Then K contains a subfield isomorphic to F, where F is the field of quotients of D. So in this sense, F can be considered as the smallest field containing D. So what this exercise asks is this: we have an integral domain D and there is a field K which contains D, and at the same time, starting from this integral domain, we can of course construct the field of its quotients, of the integral domain. Now, as we already know, this D is not necessarily or actually not a subset of F, but rather it can be embedded in F. That's the theorem we have proved in this section. So that means there is a ring which is isomorphic to D, that is a subring of F. But now we have K, which is some field which contains this integral domain. We have to now prove that there exists some field, say F prime, which is actually a subfield of K and which is isomorphic to this F. That means K contains an isomorphic copy of F. So in that sense, F is the smallest field containing D because its copy can be found in every field that contains D. So it is sitting inside every field. So in that sense, it is the smallest field containing D. That's what we have to prove. So let us see the solution, and before solving this exercise we want to make one remark also. Note that the field K containing D does not merely mean set inclusion. That is, we are not just saying, or the question does not just say that K contains D as a subset, but it says that K contains D as a subring, or in other words, K is an extension of D, but that K is an extension of D. We will now have to prove that K has a subfield that is isomorphic to F, the field of quotients of D. So consider the map or mapping, whatever you may call it. Consider the mapping, let us call it F, that we have from F into K. Note that F is our familiar field of quotients, so we know exactly what the elements in F look like. They are these equivalence classes. Okay, so one such equivalence class will look like this, where A and B are elements of the integral domain and B is non-zero. What we will do, we will map this equivalence class onto this element AB inverse. Note that since D is contained in K, any elements A and B of D are also elements in the field K, and since B is non-zero, this product AB inverse makes sense in K, which is a field. But we still have to show that this is a well-defined map, because we already know that such an element in F can have, in fact usually does have, multiple representations. So we have to make sure that the representations do not affect the ultimate result or the image. Okay, so we have to prove that if we have two different representations of the same equivalence class, we end up having the same image. Okay, since for A comma B belonging to F, we have B not equal to 0, so AB inverse actually belongs to K, and F actually maps F into K. Now consider two elements A comma B and A prime comma B prime belonging to F, such that they are equal. From this we will have to prove that their F images are also equal. That will tell us that F is well defined. Then, but from the condition for this equality, okay, let me just write it in some detail. It doesn't hurt to write a little more for the sake of clarity. So then this is related to this, and hence AB prime is equal to BA prime. That was the condition for our equivalence relation, if you recall. This in turn implies, okay, what does it imply? If I multiply both sides by B inverse, B prime inverse, I can do that, because you see, now you view this equation not in D but in the field K. So you can do that calculation because b and b prime are both non-zero, so their multiplicative inverses exist. So we ultimately get AB inverse is equal to, also we don't have to bother about the order in which we are writing the elements. That's because we are working in a field which is commutative, which is a commutative ring since it's a field. So we can write like this, and this is nothing but f of a comma b, and the right hand side is f of a prime comma b prime. Hence f is well defined. Okay, so our next aim is to prove that f is a homomorphism. Actually we want to show that f is an embedding. That we will do next. So for verifying that f is a homomorphism, we need two elements. F means small f. We need two elements in its domain, capital F. Then what about f of a comma b plus c comma d? So this is equal to, first of all we have to carry out this addition, that according to our definition of addition in capital F is AD plus BC comma BD. According to the definition of this function, this is equal to AD plus BC times BD inverse. Okay, and this can be written as AD plus BC B inverse D inverse, because we are in a field, keep that in mind. This one is in the field K. Okay, so now if we apply the distributive law, then this becomes equal to AD B inverse D inverse plus BC B inverse D inverse. This becomes equal to AB inverse, because D inverse becomes 1, which vanishes with this product. Like that, the second term is CD inverse, and this equals f of a comma b plus f of c comma d. So our function respects addition between the two fields f and k. Also, now we show that it respects multiplication. F of a comma b times c comma d is equal to AC comma BD, which equals AC times BD inverse. That is equal to AC times B inverse D inverse. Since we are in a field where multiplication is commutative and using associative law of multiplication as well, we can write it as AB inverse, I need ink. So we have AB inverse, CD inverse, and this is nothing but f of A comma B times f of C comma D. So f respects addition and multiplication, hence it's a homomorphism. Thus f is a homomorphism. We will now have to show that the kernel of f consists of only the zero element. That will tell us that f is injective. Next, let say what can I take? C. Say C belong to the kernel. I was going to write phi. C belongs to the kernel of f. Then the zero element in kernel of f, right. So that means the zero element in K, because we are mapping capital F into capital K, is equal to f of, no, what the hell have I written? Sorry about this. The kernel of f is a subset of the domain, which is our field f. So I should have taken such an element in the kernel. I don't know what I was thinking. Okay, then AB inverse, which is nothing but f of A comma B, this should be equal to the zero element in K. And since B has an inverse, if we multiply both sides by B, on the left hand side we will have A, on the right hand side we will have 0, which implies A is equal to 0. Thus, the kernel of f consists of only the zero element, which is nothing but this. Which tells us that f is injective, that is 1 to 1. But we are not done yet. Keep in mind that according to the definition of an embedding, it should not only be an injective homomorphism, that is an isomorphism, but it should also map the unit element of the domain onto the unit element of the range, if the rings have unit elements. Now, since our function f maps a field into another field which clearly have unit elements, so we have to show that the unit element in f gets mapped onto the unit element in K by small f, because otherwise, according to our definition, in spite of having an isomorphism, we can't call it an embedding. Okay. Next, for D. Okay. Oh, I think I forgot about one aspect of this problem. Just like Herstein, I think I forgot that D can be 0. What about that situation? If D is 0, then the field that we have considered is the field of two elements. Do you remember the beginning of the proof that we had previously? If D is the zero integral domain, then the field that we considered in which D can be embedded is actually the smallest possible field, which has two elements, and this clearly is contained as a subfield, or it has an isomorphic copy in any field, say K. How? The zero element of F, you map it onto the zero element of K, and the unit element of F you map onto the unit element of K. That will give you the embedding. So this is a special case which I should have started with this, but anyway, you take this as an extra note. Okay, if D is 0, then our field is this, consisting of only two elements, which is contained as a subfield or has an isomorphic copy as a subfield inside any field. Okay, and that settles the case for this, for the case where D is 0. Then we assume that D is non-zero, and for that we are doing all these things. Because I noticed it now, because now I need a non-zero element in D. Next, for any S not equal to 0 in D, for any S not equal to 0 in D, we have, recall that in the case where our integral domain is non-zero, what was the unit element in capital F? This was the unit element in capital F, which when you are thinking of this whole thing in terms of rational numbers, which is nothing but S by S, which we know is nothing but 1 or is equivalent to 1. But what does F map this onto? You see, according to the definition of F, this is S inverse, which is nothing but the unit element in K. So that's what we wanted. We wanted the unit element of F to be mapped onto the unit element of K by small f. So now we have all the pieces. Keep in mind that whatever we are doing here depends on the fact that D is non-zero, and the case that D is 0 should be settled just like that, what I have demonstrated here right now. So you write accordingly. Hence, F is an embedding and thus K contains the subfield F of F, which is isomorphic to f. By the way, why is it isomorphic to f? It's because this is our f, this is our k. We have proved that our function f is a homomorphism and one-to-one. And if instead of k we are considering the image itself, then with this as range, the function is clearly onto. So it's a bijective homomorphism, and that's why this f and f of f are isomorphic. So k contains an isomorphic copy of f. And the solution ends here. Now after this we have a system. I mean, you see what have we done in this section? We have started with an integral domain, and we have proved that from that we can construct a field in which the integral domain can be embedded. Now if we remove the restriction integral domain and we just simply have a commutative ring, and we carry out a similar procedure, what shall we end up with? Of course, it won't necessarily be a field, but it will be something. So the next exercise is about that, and it has a star, so that means it's somewhat difficult. Let R be a commutative ring. That much is given. Or something else is also given with unit element.